Welcome back to another episode of Dominic Does DIY. Don't forget to click subscribe and share, and thanks to all those who have subscribed and come back to see the next videos. So without further ado, let's go ahead and get in with the video. So today the boss comes in and requests from you a simple current source circuit. He needs it to drive a laser diode, and the laser diode will vary in output voltages of 1.7 volts to 3 volts depending on current and temperature. The nominal operating current of the laser diode is roughly 350 milliamps at 2.7 volts, and we'll want to operate under these conditions. Today we have a more restricted number of components, and the question is, can we do it with the components we have available, or do we tell the boss we need to place a DigiKey order? We have the following selection of components. We have one op amp, we have one 2N4403 from onsemi, we have one laser diode for the load, which is the 350 milliamps at 2.7 volts. This will be represented by a resistor when we go to simulate. We have a 2 ohm 1% quarter watt resistor. We have a 1 ohm 1% 1/8 watt resistor. And we have a 500 milliohm 1% 1/10 watt resistor. We also have at our disposal a 10K, a 365 ohm, a 750 ohm, and a 1.6K ohm resistor, 1% at 1/16 watt. Pause the video now if you would like to work it out on your own. Otherwise, hang tight for a second and I will go over it. I'll leave a link for the 2N4403 transistor in the description. First, we need to understand the basic circuit we will use, then we can start understanding what we have and what we have to do. So we'll construct a basic current source using an op amp and the BJT. The way this works is you have the op amp controlling the current through the base of the PNP to regulate the VCE of the PNP. Since the op amp keeps N minus equal to N plus, we have created a current source with R23. With VCC equal to 5 volts, we have a voltage divider setting the voltage at N plus and thus N minus. So IS is going to equal VCC minus the V feedback, which is our N plus pin, all over the set resistor. Let's start with the basics in the spreadsheet and our knowns. We know we have a VCC equal to 5 volts. We know that our load for the laser diode is 350 milliamps. And we know that we will use the 10K resistor as a pull down resistor, RG, for the N plus pin. So in this schematic, it happens to be R26 is our RG. So let's see about the rest of these resistors. The voltage feedback is a basic resistor divider. So our RS is going to equal the formula I have right here. So we know RG, we know VCC, and we now need to just calculate voltage feedback, our VFB. So what is our VFB? Well, since we know that our VFB is N minus, and we know that N minus is equals to N plus, well, how do we get the N minus voltage that we want? That's simply the voltage drop across our RS, our R23. So how do we get the voltage drop across that? Very simple. We just take our drive current, the 350 milliamps, and we multiply it by our set resistor, and then that'll give us our feedback voltage that we want. So the feedback voltage would then be VCC minus IS times RS, or basically VCC minus our drive current and R23. So what values are we going to use for the RS, for our set resistor? It's going to be the smaller current sense resistor values, like the 500 milliohm, the 1 ohm, or the 2 ohm that we're going to stick in place for the R23 and see what we get as a result. So we'll put those values in. It'll tell us what our VN plus is, our V feedback, and it'll tell us what our input resistor is, which is the R25. So now using our spreadsheet, we can go through and use these different set resistors. The first one we have is our 2 ohm resistor for our set resistor, and that gives us an RN and R25 of 1.6K. Next, we have our 1 ohm resistor. That gives us a V feedback of about 4.65 volts, and it allows our input resistor, our R25. That one is going to be the 750 ohm resistor. And then finally, our 500 milliohm set resistor, and we can see that that is about 365 ohms with a V feedback of about 4.825. So now we have our resistor pair set up. We know that 2 ohms is 1.6K, 1 ohm uses the 750 ohm, and the 500 milliohm uses the 365 ohm. And right now it all seems to mathematically work that we can use any of these resistors and get the results that we want. But do they actually work in the system? Right? One thing is with math, the other one is in real world. So we need to actually check some tolerance stackups and some wattage usage and see if these resistors or what set of these resistors is the best option. So all the resistors we know are 1% resistors. So I have my tolerance 1% right here. And for each of these resistors, our Rn we calculated, we're going to start out with the 2 ohm resistor. So we know that our Rg, our R26 was 10K. And we know that with a 2 ohm resistor for our set resistor for our R23, we calculated out as a 1.6K for our Rn, our R25. And so when we do that, we got to take into account first our min and our maxes. So 1% resistor, we just get our mins and our maxes for all of the resistors. And then we can calculate our voltage drop, our min and our max based on the voltage drop. And then from that, we can calculate our minimal current draw that we will see. So remember, we had a requirement of about 350 milliamps. I chose a 1.6K resistor, but if you remember the calculation, it was more like 1.63 or something like that. So our drive current is a little bit low. So we can see though that we get a pretty large range on our current draw. Now what we need to pay attention to with these resistors, because if you remember correctly, the 2 ohm resistor was a quarter watt resistor. So the question is how much wattage are we going to see on this resistor under this load? So we know that the wattage is just V times I. So if we just scroll down a little, we can see that our power calculation here, we're going to see anywhere between 227 and 249 milliwatts, which is more than a quarter watt. So this resistor, while mathematically it works, it is not good for this system because it is only a quarter watt resistor, but we're going to push more than a quarter watt of power through it under all of the circumstances with the tolerance stack up that's going on. So this one is not good. This is not the proper solution. So we can knock the 2 ohm off of the table. So now let's just go up and we're going to check out the 1 ohm. So the 1 ohm, and the 1 ohm, it used the 750. It used the 750 ohm resistor. We're actually getting a little closer to our drive current of 350 milliamps here, right? Going from 339 to 360, but at least our nominal is in the 350 range because we were a little closer on this one. And when we look at our wattage output, remember this one was 125 milliwatt resistor. This was a 8th watt resistor, so 125 milliwatts. And you can see here, for the most part, 5% of the time, this system would work. But we have this one resistor up here, this one high range, right? Under an extreme condition, we can actually see a maximum output of 128 milliwatts. So this actually goes over the rating of the 8th watt resistor. So we don't want to use this one as our primary source until we check out the last one. Let's take a look at the last one, which is the 500 milliohm. And with the 500 milliohm, that one actually used a 365 ohm resistor. And so when we look at this one, we can see using the 500 milliohm with the 365 ohm R25, our milliwatts is under 100 milliwatts. And this particular resistor was rated at 1/10 of a watt. So the 500 milliohm 1/10 watt resistor is overrated for this application. So this is the proper system. These are the proper resistor sets to use for this application so we don't overheat a resistor and possibly blow out the resistor in the system. Now we just need to confirm the PNP will not exceed any power limits. Since we know the laser diode is 2.7 volts at 350 milliamps, then the PNP has to pick up the leftover voltage drop. So our VCE of the BJT, it will equal to the VCC minus the voltage drop across our set resistor minus the voltage drop across the load. When we look at the datasheet of the BJT, we can see it's a TO92 package, and it has a maximum junction temperature of 150 C. So this is the maximum temperature that the junction can get, and we cannot exceed this. It also has an RJA of 200 degrees C rise per watt. So our power dissipation is basically the drive current times the VCE. And when we do this with our 500 milliohm resistor, we can see that the power dissipation across this is anywhere from 531 to 563 milliwatts. And now to calculate the junction temperature, we just take our ambient temperature plus RJA times our power output, and that'll give us our junction temperature in C. And so long as this number is less than our maximum junction temperature, then we should be good to go in using this component in the system, and it should not overheat. So right now it looks like the PNP, according to the numbers, looks like it will be just fine handling this load. Let's just run the simulation to prove that we indeed have a constant current source over the voltage range of the laser diode. So for the load resistor at 350 milliamps, the load resistor will go anywhere from 5 to 8.5 ohms to represent the laser diode. And the nominal voltage for our 2.7 volts out will be about a 7.8 ohm resistor. So we'll just run it using those values. And let's go ahead and add all the values for our actual resistors. So our set resistor was a 500 milliohm. Our R25 was a 365 ohm. Our R26, this was a 10K. And so we'll just look at our nominal voltage first. That's about a 7.8 volts. So let's run it. So we can see here at 7.8 ohms, which represents basically our laser diode at nominal, we have a 350 milliamp drive current and 2.73 volts as an output. So it works. But remember, this thing can go anywhere. There's a wider swing voltage range on this laser diode as it heats up and whatnot. So let's just see if we can continually push 350 milliamps, even though the load changes. So we'll go ahead and change this to about a 5 ohm load and run it again. You can see that our drive current does not change, but the voltage drop across that resistor, it does change. So it went from 2.7 down to about 1.75. And if we change this again to 8.5, which is the upper range of the laser diode, and run it, you can see still 350 milliamp drive current, but the voltage drop across the load is now around 3 volts. So no matter what our load is, up to a certain point, we'll be able to push 350 milliamps to the load consistently. And the only thing that'll change is the voltage drop across Q1 is what will compensate for that differential. So the one limitation that there is on this setup is as your load voltage, when you're driving the current, as your load voltage starts approaching your VCC or your V feedback, and you can no longer have a sufficient voltage drop across your PNP, across the transistor, then you're no longer able to regulate current like you should, because now you're just going to end up with your input voltage equaling your output voltage, and you're just going to start dropping current. But up until that point, we have a constant current source right here. So there we have it. We do not need to order from DigiKey anything using the 500 milliohm and the 365 ohm resistors. With the PNP and the op amp, we can achieve the goal the boss wants. So I hope you enjoyed this episode. And if you did enjoy it, please again, like, subscribe, share, and leave a comment down below if you have any comments. And I'll see you next time. And always remember, The best way to get good is by doing stuff. So keep doing stuff and getting good.